I'm going to be talking about seagrass and macroalgae as nature-based climate solutions, where I mapped blue carbon ecosystems in Norway. So first, let's talk about the importance of blue carbon. Most people picture forests and plants when they think about natural carbon storage, but some of the most efficient carbon sinks are actually in our oceans. Blue carbon ecosystems are coastal vegetated ecosystems like mangroves and seagrass that are able to store and sequester atmospheric carbon, sometimes at rates even faster than our terrestrial forests can. Although they cover less than 2% of the seafloor, they account for 50% of storage of all sediment carbon in the ocean. The problem is that despite how powerful they are as carbon sinks, sometimes they're entirely overlooked in how countries account for carbon. And that gap is what my capstone is about. So I got the opportunity to collaborate on the Sea Blues project, which is an EU-China joint research consortium across 12 countries, all focused on advancing what we know about blue carbon. It's coordinated by the Norwegian Institute of Water Research, or NIVA, who is my primary capstone stakeholder. And here's all of us in Greece just a few months ago, where I got to attend the annual meeting and discuss cutting-edge blue carbon science with the whole team. So I focused on Norway, obviously, as my case study, and I was lucky enough to travel to this beautiful country and work hands-on with the experts at NIVA. Norway is an extremely compelling case study. As you can see, it has a huge coastline, which is dominated by seagrass and macroalgae as their dominant coastal vegetated ecosystems. And its government has expressed a lot of interest in blue carbon, which they call their blue forests. But these ecosystems are extremely complex, and that's why it's such an interesting implementation challenge, bridging the science to the policy. So Norway has macroalgae, which include kelp forests like this one, as well as rockweed like this, which are both found on rocky substrate. In contrast, seagrass is found in softer, sandy, or muddy sediments, and this difference is key because how they store carbon is completely different. Seagrass buries carbon in the sediments directly beneath the habitat, whereas macroalgae bury their carbon non-locally. It's exported out into the deep sea and buried there. So by studying both of these ecosystems, I'm capturing two prominent but highly contrasting carbon pathways in Norwegian waters. And remember this contrast because it drives a lot of the results to follow. So beyond carbon, these ecosystems also host a whole variety of co-benefits, such as fisheries and nurseries habitat, wave attenuation and coastal resilience, biodiversity, nutrient cycling, just to name a few. These ecosystem services are highly essential, but they're also super relevant to blue carbon policy because they offer financing mechanisms. But human pressures also greatly impact their ecosystem function. These habitats face threats from fishing, dredging, coastal darkening and eutrophication from runoff, marine litter, anchoring, coastal infrastructure, just to name a few of our anthropogenic activities that we do that mess up these ecosystems. And this is super important because it also messes with their ability to store carbon. So why do we care about carbon accounting, and why do countries care? Because what gets accounted is ultimately what gets managed and what gets noticed. Countries report their emissions and removals through greenhouse gas inventories, such as this example from Norway. On the positive y-axis, you're seeing some of Norway's emissions broken down by sector, but you also notice this section here which goes into the negative, and that's their carbon removals. And this category that I've highlighted is land use change, and forestry. There are now methodologies for wetlands, yay, but the problem is that blue carbon doesn't always actually fit into this methodology. Sometimes it's not compatible, or countries simply aren't choosing to implement them. And this is important because if these ecosystems aren't put in these inventories, then their losses are essentially invisible, and so is the benefit of protecting them. So to understand the role of blue carbon ecosystems in climate change mitigation, you can think of these ecosystems like bank accounts that have been filling up for centuries, something we wish we all had, right? So the carbon that's stored long-term in these ecosystems is like the bank account balance. And just by existing as healthy habitats, These habitats can basically earn interest, just like money sitting in the bank, pulling down extra CO2 from the atmosphere year after year and adding that to the existing balance. So the stronger the ecosystem, the bigger the balance, and the more interest it earns. And that's what this schematic is showing, and it's specific to Norway. So you have rockweed, seagrass, and kelp that all fix CO2 from the atmosphere through photosynthesis, shown here as their net primary production, or NPP. And this carbon is often just remineralized back as CO2 into the system, but some of it is sequestered long-term, and that's the carbon that we care about. For seagrass, it's sequestered as particulate organic carbon directly underneath the sediment, but for macroalgae, it's exported to the deep sea and buried as particulate or dissolved organic carbon. And so what this schematic is really revealing is that the long-term storage of these ecosystems is equivalent to 2% of Norwegian emissions. That number alone is huge. But what if we flipped it around? What if all of these ecosystems were lost because of all of our anthropogenic pressures? It would release 33 million tons of CO2 and lead to the loss of nearly 4 million tons of CO2 uptake every single year. That's that interest I was talking about. And that's the key issue. These fluxes aren't accounted for in Norway's climate commitments or their inventories, at least not yet. So this brings us to my research questions. I'm analyzing what the current distribution, carbon evidence, and ecological context is, the environmental drivers and human pressures that shape these ecosystems' potential, how they differ in their scientific and their policy readiness, and then what monitoring and governance gaps exist, limiting their ability to be implemented into policy. So I accomplished this by creating two databases, one for seagrass and one for macroalgae. I started with site-level data compilation, and then I aggregated that to the regional and national levels. I combined my data files with external spatial layers, ran that through Python real easy, and created an interactive map of Norway, showing all of its blue carbon and the variables of interest. And then from there, I was able to do my data analysis, which was mostly spatial co-location. So here's the central deliverable of my capstone, the interactive Norway map, and I'll run through briefly kind of how it works. So first I'm toggling on my study sites for seagrass and macroalgae, and then you can see on the left side panel all the data source information and legends that's gonna explain everything. And then on the right is layers broken down by category. So you can pick which category you're interested in. For example, right now I'm adding sedimentation rates and regional summaries for carbon. There's also the environmental drivers. So this is sea surface temperature as well as sea surface salinity. And then all of the human drivers that I was mentioning earlier, you can toggle those on: ocean darkening, port vessel activity, and dredging effort, just to name a few examples. So now we're going to dive into southern Norway to look at some more specific details of the map. So here you can see summaries from the Oslofjord and the Skagerrak coast, and then you can also see kelp and seagrass sites. Then zooming in even further, we can look at some spatial co-locations. So the blue is showing kelp extent, and the green is showing seagrass extent. And then the colored polygons are the co-location. So this is showing a protected zone, but it's still facing 12 pressure signals, and it's nearby to seagrass sites. In contrast, this polygon shows 0 pressure signals, but the same protection. So you can see how highly variable it is, even within this very small scope. Toggling on the marine protected layers, we can see where those are. And then you can jump over here and see that this area falls outside of that protection zone, but it still faces pressure signals. And so the point of my mapping is basically central to my results. And the intention is to demonstrate how this kind of co-location analysis can be utilized by policymakers to understand the current science that exists, the data gaps, and so that they're able to assess the next steps. So I'll go over a few of the key results that I derived from the mapping and the data analysis. First, macroalgae have a much larger extent than seagrass, roughly 10,500 kilometers squared for macroalgae versus 90 kilometers squared for seagrass, which is driving the results that you're seeing in panel A, which is the carbon pools. And this is about a 1.5 order magnitude difference for macroalgae versus seagrass. And then panel B shows sequestration rates, which is about a 2 order magnitude difference between macroalgae and seagrass. But the key thing is that these are fundamental, there are fundamental differences in the type of carbon that we're seeing here. For seagrass, all of these values represent true sequestration. Sure, there's a little bit of uncertainty, but the macroalgal carbon is much more uncertain and it's continuously fluctuating. So we're not sure how much of that is actually being stored long-term. And all of this means that you can't account for carbon in the same way for these two blue carbon ecosystems. You can even add sequestration values if you'd like. Panel C shows, for example, like the social cost of carbon for the sequestration. But jumping back to panel B, you can see the error bars, and macroalgae has a much larger bar, which shows that it has a much higher uncertainty, and that carries over into the sequestration values and any other metrics that you're looking at. Panel D also shows some important results. Basically, the resolution difference matters a lot for policy. Seagrass scales to the regional level, but as you can see, it's very highly regionally variable, which matters a lot when you're looking at a national scale inventory. And macroalgae actually doesn't scale to this level. Carbon data was only provided at the national level, which is also a huge data gap. So quantifying the uncertainties and the data gaps embedded is also another key result because those determine whether each ecosystem is ready for formal accounting. The next analysis comes from overlaying pressures, protection, and carbon. First, in panel A, you can see looking at carbon, pressure, and protection. Pressure is kind of an interesting finding. Seagrass, the bottom three panels, show a lot more pressures than what kelp face. So seagrass face roughly 16 to 53 pressure indices per kilometer squared versus under 5 for all of macroalgae. And then another key finding is that the worst case scenario in Norway is actually for seagrass in southern Norway, which is the region I showed you on the interactive map. And it's that bottom pane right there. You can see that the majority of carbon in seagrass is stored in the southern region, but this is the region that also faces the most pressure and the least protection. And then panel B decomposes the pressures by the actual pressure type, so you can see what it's facing, like dredging, aquaculture, and fishing effort. And this analysis signals for policymakers where they should focus. And on the next slide, I turn it into a screening analysis. So these screening classes basically rank the areas by management priority, and the most obvious or striking result is pretty obvious in this first panel. There's no carbon that's considered the most safe category, which is where there's low pressures and lots of protection. Instead, most of the carbon falls in a low pressure zone, but it's unprotected, which means that it's vulnerable. And the rest of the carbon is already facing high pressures. And if there's no protection and a lot of pressures and we're losing these ecosystems, then they're not able to function their best. And none of that is being accounted for right now. So this signals to policymakers that protection needs to happen immediately. And lastly, I'm going to uncover this figure piece by piece. It's essentially the heart of my project where I turn the science into a policy roadmap. So these are the existing tools or frameworks that can bring blue carbon into national governance. First, there's the IPCC wetland supplement, which is the main methodology for accounting for wetlands and greenhouse gas inventories. Some blue carbon is compatible, but some isn't. This is then reported to the UNFCCC, which also has some blue carbon financing mechanisms. At the country level, there's nationally determined contributions, which are flexible climate goals. And then there's UN Sustainable Development Goals, 2 of which apply directly to the oceans. And Norway also has a whole host of national marine and biodiversity policies that are applicable. So secondly, the crucial aspect is that seagrass and macroalgae don't fit into these tools equally. And these tools can basically provide policy entry points, but these are going to differ by ecosystem because the science is so different for these two. So seagrass fits most directly into the IPCC template, and I would argue that it's nearly ready for formal accounting if it can address some of those data gaps and enhance monitoring, whereas macroalgae doesn't fit the standard template for the IPCC. And this means that they would have to develop their own unique methodology as a country, which has only been done in one other country so far recently. So it's a highly novel process. And third, I propose a phased differentiated pathway for implementation. This is my primary finding. Basically, seagrass can start immediately with basic tier 1 accounting and then work its way up to more advanced accounting over time, adding co-benefit policies as you go, whereas macrobiology would have to start at the opposite end where the science is the strongest with biodiversity, adaptation, and other marine regulations, only adding in the carbon accounting as the science matures. And basically the key takeaway is that blue carbon policy needs to encompass the entire carbon, biodiversity, coastal resilience nexus rather than just focusing on the carbon benefits. And that policy needs to be enacted now to protect these ecosystems, but that happens on different timelines. And finally, if you guys would like, you can scan the QR code here and access my public GitHub repository, which contains my interactive map, and it contains all of my data analysis in a reproducible workflow. No pressure if you are not interested. But the whole intention was to give Sea Blues and NEVA something concrete to build on for the next steps of blue carbon policy and science. So I have so many people to thank. But I'd like to start by thanking Richard Bellerby and Mark Merrifield, my advisors, as well as Corey and Jada for their support this entire year. There were so many other scientists and professors at Scripps and at NEVA and at Sea Blues that all helped contribute. Also, big thank you to the Julia R. Brown Fund for helping me go to Norway and Greece to conduct my findings. And lastly, thank you to my wonderful, beautiful cohort who has supported me and inspired me this entire year. So thank you.
Thank you so much. This was such a wonderful and very, very impressive project. After scanning your QR code and talking to you a bit about your project throughout its development, I noticed that you had a couple of deliverables that you may not have had time to mention in your project. Would you like to speak on any of those?
Yes. So originally, as the Sea Blues project encompasses pretty much all of Europe as well as China, I actually built an interactive map for all of Europe as well. But I didn't include it because it has some data that hasn't been publicly released yet from the Sea Blues project. So once Sea Blues gives me the go-ahead to make it public, I will add it to my GitHub, and that QR code will also have that. So it's not just Norway, it's all of Europe. But yeah, so thank you for that question.